In the last lecture, we have seen two new kinds of compactness, that of limit point compactness and sequential compactness. And we proved that compactness implies a limit point compactness even for general topological spaces. This is for arbitrary topological spaces. And we have also seen that limit point compactness implied sequential compactness, but this was only for metric spaces. And what we want to show in this lecture is that sequential compactness implies compactness for metric spaces again. So in fact, for metric spaces, we have compactness implies limit point compactness implies sequential compactness, and sequential compactness implies compactness. Therefore, all three are equivalent. So these are equivalent for metric spaces. And so for this lecture, we will try to show that sequential compactness implies compactness for metric spaces. So we shall begin with a counterpart for the Lebesgue number lemma that we proved for compact spaces, and we will show that if a topological space is sequentially compact, then it has the Lebesgue number property. So let us start with that property. So our theorem, first theorem will be that sequentially compact space X is has the Lebesgue number property, has the Lebesgue number property if X is metrizable. So we restrict our attention to metrizable spaces or metric spaces if you want, and we will show that any sequentially compact metric space has the Lebesgue number property. So recall that the Lebesgue number property meant that every open cover A of X has a Lebesgue number. This means that there exists a delta greater than 0 such that for any set A of diameter less than delta, then there exists set B in this open cover such that A is a subset of this open set B. So we gave two different formulations of this Lebesgue number. So one was using metric balls and one was using sets of diameters less than some threshold number delta. And so we are going to use the second one with the diameters. And so we have to show that if X is sequentially compact, then it has the Lebesgue number property. Of course, X is supposed to be a metric space. Notice that we want to we have already shown that a compact space has the Lebesgue number property, and we want to show that a sequentially compact space is compact. So we cannot use the Lebesgue number property directly because well, we don't know that X is compact yet. So let us see a proof of this theorem. So for this proof we will use the contradiction method. So we'll argue by contradiction. So suppose that A is an open cover of X, which does not have a Lebesgue number, which does not have a Lebesgue number, and this means that for any delta greater than 0, there exists a set C delta of diameter less than delta such that C delta is not contained in any element B of this open cover A. And if this is true, then this means that for each natural number n, there exists a set Cn of diameter less than 1 by n. So we are just choosing n large enough, so we can have a set of diameter less than 1 over n such that Cn is not contained in any element B of A. So now we will try to use this to get a contradiction using the sequential compactness of the metric space X. Now for each n, choose for each natural number n, let us choose a point xn in Cn. So this is possible since this is possible since none of the Cn's are empty, because if any of the Cn's are empty, then Cn must be contained in not only one but every element of the open cover. So all of them must be non-empty, and so we can choose for each n a point xn in Cn, and consider this sequence of points xn. And now we are going to use the sequential compactness of X. So by the sequential compactness of X, xn, this sequence xn has a convergent subsequence, say xni, okay, I in n, and suppose that this sequence xni converges to some point A in X. Now this point A, since this collection A covers X, so this is an open cover of X, there exists some B in A containing this point A. So A belongs to B, and because B is open, So there exists an epsilon greater than 0 such that the metric ball with center A and radius epsilon lies inside this set B. On the other hand, this means that now we can choose I large enough such that 1 over Ni is less than epsilon by 2. So this is possible because Ni is a strictly increasing sequence of natural numbers. So there will be a large enough index in I for which Ni 1 over Ni is less than epsilon by 2. So here epsilon is from the radius of the basic neighborhood around A. And this implies, so the set CNI, which has diameter with diameter less than 1 over Ni, so it has diameter of CNI is also less than epsilon by 2. This means that CNI lies inside the metric ball with radius xni and radius epsilon by 2. So this was the first part, and now we are going to choose xni close enough to A such that CNI will lie completely inside this metric ball BDA epsilon, and which will be completely inside this open set B from this open cover, and which will contradict our assumption that CNI is not contained in any of the open sets from the collection A. So now we are going to choose Ni again, choose I large enough that so along with this star, which is 1 over Ni less than epsilon by 2, says that star is satisfied along with the property that the distance between x and I to A is less than epsilon by 2, and this is possible since the subsequence xni converges to this point A. So you have let us draw some picture here. So here you have A, and here you have a sequence of points. So this is xni converging to this point A. This is xni. Now we have chosen a metric ball of radius epsilon around A. So suppose that this is the metric ball of radius epsilon around A, and now we know that this subsequence becomes closer and closer to A because it converges to A. So, and if for each of these xni's you can have the set CNI. So suppose that this one is our xni for which 1 over Ni is less than epsilon by 2, and for this one we have this set CNI which contains xni. So CNI contains xni, and it has a diameter, the diameter of this set is less than epsilon by 2. So therefore if the distance between A and X is chosen to be also less than epsilon by 2, if this distance is chosen are less than epsilon by 2, then by the triangle inequality we will have that the whole set CNI lies completely inside this metric ball of radius epsilon around A. So this is what we did. So the first index we chose was I large enough such that 1 over ni is less than epsilon by 2, and the second one, so Cni is a subset of the metric ball of radius epsilon by 2 with center xni. On the other hand, since xni converges to A, then we chose ni large enough such that the distance between xni and A is less than epsilon by 2. So let me denote this as star point 1, and now we will use star and star point 1 imply that for any point z in Cni, we have that dAz is less than epsilon, and this is because since dAz is less than dAxni plus dxni comma z, and the first one is less than epsilon by 2 by star point 1, and the second one is less than epsilon by 2 by star. So the adding these things up, we will get less than epsilon. So Cni, so this means that Cni lies completely inside the metric ball of radius epsilon and center A, and we have chosen this so that it lies completely inside this set B from this open cover, which is a contradiction. So this means that A has a Lebesgue number, and so X has the Lebesgue number property. So we see that a sequentially compact metric space has the Lebesgue number property. Now we will use yet another property which is called totally boundedness. So let us define what is totally bounded. Totally bounded metric spaces. So a metric space XD is called totally bounded if for each epsilon greater than 0 there exists a finite open cover of X by metric balls of radius less than epsilon. So of course these are open metric balls because we are considering open covers. So but the point is to have finitely many, so we must have a finite subcover of any open cover where each of the open sets in the open cover has a radius less than epsilon. So this is what's called a totally bounded metric space. And what we can, so of course the first theorem that we can state is that the compact spaces are totally bounded. A compact metric space is totally bounded, and this is quite easy because if you choose A to be the collection of all epsilon balls, so of course suppose that given any epsilon, so let epsilon greater than 0, and then you choose this open cover which is the collection of all metric balls with points in X and radius epsilon. So this is and this is an open cover of X. And now because of compactness, since X is compact, there exists a finite subcover, and this is what totally bounded requires. You want a finite subcover of X by open metric balls of radius less than epsilon. This means that X is totally bounded. And so this part is easy. What we will also show is that a sequentially compact metric space, a sequentially compact metric space is also totally bounded. So to prove this, suppose to the contrary. So suppose that there exists an epsilon greater than 0 for which no open cover of X with open metric balls of radius less than epsilon can have a finite subcover. So now we start by constructing a sequence so we will show that in this case there is a sequence, there exists a sequence xn which has no convergent subsequence, and if we show that, we will in particular we will show that the sequence xn will satisfy the property that the distance between any 2 points xn and xm is greater than or equal to epsilon for all n m in n and not equal to m. So any two distinct points must have a distance greater than or equal to epsilon, which means that if there exists a subsequence x and I converging to some point, let's say x star, then the epsilon neighborhood of x star can contain only one xn from this sequence, so which is a contradiction, since we have assumed x and I to be converging to x star. So every epsilon neighborhood must contain infinitely many of these x and i's. So this is a contradiction. So we will construct this sequence xn for which any 2 points must have a distance greater than or equal to epsilon. So since we have that no open cover of X with open metric balls of radius less than epsilon can have a finite subcover, so this means that choosing an arbitrary point, choosing x1 an arbitrary point, then BD x1 epsilon cannot cover X. So this is simply because if it did cover X, then there will be a finite open cover of X with metric balls. So this is not possible. So by our assumption, so this means that there exists a point x2 belonging to the complement of this metric ball of center x1 and radius epsilon. Now we have a recursive definition. So recursively, if x1, x2 up to xn are chosen, then the point xn plus 1 is chosen such that xn plus 1 belongs to the complement of the union of all these metric balls, the xk epsilon k from 1 to n whole complement. So this is possible again, since x is not equal to the union of the finitely many epsilon balls bdxk epsilon. By hypothesis, this is not possible, so we can choose a point in the complement. And this sequence, the sequence xn defined as above, defined like this, satisfies the property that d of xn xm is greater than or equal to epsilon. This is because we are choosing xn plus 1 away from each of these xk's with a distance more than epsilon. So therefore dxn xm is greater than or equal to epsilon for all n m distinct in the natural numbers. And this leads to a contradiction. So this means that this is a sequence without a convergent subsequence, and this means that your space X, which is a contradiction, this is a contradiction, since X is sequentially compact. So we see that a sequentially compact space is also totally bounded. And now we are ready to prove the initial theorem that we wanted to prove, which is that a sequentially compact space, sequentially compact metric space is compact. So let us see a proof of this theorem. So to prove this, suppose that A is an open cover of a sequentially compact space X, and now A by the Lebesgue number property. So by the Lebesgue number property, we have shown that a sequentially compact space has the Lebesgue number property. So this is theorem 4.1 above. So this open cover A has a Lebesgue number, say delta, and with this Lebesgue number, let epsilon be the number delta over 3. Now using the totally boundedness of X, which is theorem 4.3 above, we obtain a finite cover of X by open epsilon balls. So we have seen that sequentially compact space is totally bounded, and therefore for each epsilon there exists a finite cover of X by open epsilon balls. So for this particular epsilon also there exists a finite open cover of X by epsilon balls, open epsilon balls. And now any such open epsilon ball will have diameter less than 2 delta by 3, so which is 2 epsilon. So if a metric ball has radius epsilon, then it has diameter at most 2 epsilon. Okay, so any such open epsilon ball will have diameter less than 2 epsilon, and because this is less than delta, 2 delta by 3 is less than delta, strictly less than delta, and this means that such an open ball, epsilon ball, is contained in some open set in A. This is by the Lebesgue number property. By the Lebesgue number property, every set of diameter less than delta will be contained in an open set from the collection of sets in the open cover. So therefore, so if we choose one such open set in A, for each of the finitely many open epsilon balls, we obtain a finite subcover of X. This is because we have a finite subcover of X by open epsilon balls, and each of these open epsilon balls lie in some open set in this open cover A. Therefore we have a finite subcover, and this means that X is compact. So we have shown that sequential compactness implies compactness for metric spaces.